Hello everyone, good morning. Let's start for today's class summary. So thanks for a classmate of the class who has figured out some typos in this lecture slide. So we will first go over the lecture slide typos first. Okay, so let me see. We'll enter full screen. Okay. So today we will be continuing our discussion on the generating functions, but then after that we will start something new, the recurrence relation. Okay, so first of all, let's check the typo. So there was a typo somewhere else before. Excuse me. So let me double check the type. Where is the location of the typo first? Okay, here it is. So this is page 28. So this is a corrected version already. So if you download the slides now, so it will be corrected. So here, originally it was written on page 28. It is the number of ways to distribute R non-distinct items into non-distinct cells, but it is not correct. It is still R distinct items into N non-distinct cells. Okay, so items are still always distinct. The non-distinct case will be talked today. Okay, so up to this point, it is non-distinct. Okay, and there are some more typos that I will show you as along the way when we are talking about today's class. Okay. Okay, so today's focus will be about distributing non-distinct objects into non-distinct cells. So in particular, this is just like a partition of integer into positive integral parts. It is because when objects are non-distinct and then the distribution is also into non-distinct cells, what we care is how many items in a certain box and how many items in the next box, and we don't care about the ordering. So in that case, it is just like I'm looking at what are the different ways that I'm trying to partition a certain integer, and there are some rules that depends on the cell's requirement. So for instance, suppose that let's say we have unlimited number of cells. So all the cells are non-distinct, but they are unlimited. And then there is no restriction of how many objects we can put into a certain cell. So in this case, this corresponds to the integer partition problem. So for instance, if you have the integer 4, the different ways of cutting 4 into parts is 4 itself could be one way, or we can have 1 plus 3, so that 4 is divided into 2 parts. One of them is 1, the other is 3, and we don't care about the ordering. So 1 plus 3 would be the same as 3 plus 1. Okay, and then we can also have 2 plus 2, and then we could also have 1 plus 1 plus 2, and then finally it is 1 plus 1 plus 1 plus 1. So here we are distributing 4 into 4 parts. Each part is 1. And these are all the 5 possible ways to partition the number 4 into positive integers sum. Okay? So this is corresponding to partition 4 non-distinct objects into non-distinct cells, unlimited number of non-distinct cells. Okay? Okay, so to do the corresponding counting problem, we will need to go back to the generating function, the ordinary generating function, rather than the exponential generating function. Yeah, it is because now the ordering of the objects doesn't matter. So perhaps it makes more sense that we will be using the normal generating function rather than we count the permutation. Okay, so if you still recall, 1 plus x squared plus x3 up to xn, it can be used as the as showing if I want to have an integer that is partitioned with exactly k ones, so there is one way that I can have 1 1. I can have one way that I will have 2 ones, I will have one way that I will have 3 ones, and so on and so forth. So perhaps let us jump to this particular example, and we'll see what is actually going on. So let's consider this particular function fx. So fx is equal to 1 plus x squared plus x cubed multiplied with 1 plus x squared plus x4 plus x6 multiplied with 1 plus x3 plus xx plus x9, and so on and so forth. So up to 1 plus xn plus x2n plus x3n, and so on and so forth. Now suppose that we have this function x, this generating function x, and let us also consider the case where we want to find out what is the coefficient of x to the power 4 in the resulting formula. And here we let n to be some large number. Let's say n is equal to 100. Okay. Now, in order to get the coefficient x of x to the power 4, so we need to find that all the different ways such that the product here of this polynomial, we will get x to the power 4 as a result. Now, to get x to the power 4, one way is I choose this one, I choose this one, I choose this one, and then when they are multiplied with x to the power 4, I can get x to the power 4. All the remaining parts, we will assume that we are going to choose 1. So there is one way corresponding to 1, 1, 1, x4. And then there is another way. For instance, I can choose 1, and then x4, and then 1, and then 1. This will also give us x4, right? And then there could be another way. For instance, I could be choosing x squared here, I could be choosing x squared here, I could be choosing 1 here, I could be choosing 1 here. Now, all these different ways are corresponding to how we can partition 4 into the different parts. Okay, so let's examine the last example. When we are having x squared, 1, 1, what does that correspond to? So notice that the power of x is increasing 1 by 1 here. So we are actually using this to specify how many ones are there that will appear in the partition of the number 4. So we are using 4 as an example. So here this is saying that 1 means we are not using any of the 1 in the partition. Here we are using exactly 1, 1. Here it means that we are using exactly 2 ones, and here we are using exactly 3 ones, and so on and so forth. And similarly, this second one, this second polynomial here, it corresponds to the number of 2's that we are going to use in the partition. So this is not using any 2, using exactly 1 2, exactly 2 2's, exactly 3 2's, and so on and so forth. And then the third one here corresponds to the number of 3's that we are using in the partition, and so on and so forth. This is number of 4's that we are using. So when we have a combination of getting x squared here, 1, 1 here, we are choosing 2 1's and 1 2, and 0 3 and 0 4. So it corresponds to 1 plus 1 plus 2, and this is a way to partition 4. Now, if I want to get a partition of 4 into 1 plus 3, so how would that be? So we are going to choose this x here because we are choosing 1 copy of 1, 0 copy of 2, 1 copy of 3, and 0 copy of 4. So 1 plus 3 corresponds to something like this. We are choosing this x to the power 1 here and x to the power 3 here. Now, how about 1 plus 1 plus 1 plus 1? So in this case, we are choosing 4 copies of 1. Then in that case, we are choosing x to the power 4 in the first polynomial, and then 1 here, and then 1 here, and then 1 here, meaning that we are not choosing any. We are not choosing any copy of 2, any copy of 3, any copy of 4. Now, if we understand this one, then this is a very interesting thing to talk about this particular generating function. So this generating function will give us a polynomial that has in the form of 1 plus some number of x plus some number of x squared, and so on and so forth. What is the coefficient of x to the power n here? Now, if I want to get the coefficient of x to the power n, or coefficient of x to the power anything, like x to the power r, then the coefficient of x to the power r, it means that we are finding the total number of ways to partition the number r, but then we have restrictions. We can use any number of 1's, any number of 2's, any number of 3's, up to any number of n's. But we cannot use n plus 1 as a part. We can use n plus 2 as a part, and so on and so forth. So here, this is the last polynomial that we are seeing. So in that case, this limits the size of each part. So a particular part cannot exceed n. Now, if I want to do something that is even more general, so we don't have any restriction, I want to find out how many ways that we can partition a certain number R, and then there is no restriction of the size of each part, then the corresponding generating then the corresponding generating function will be what? The corresponding generating function will be the corresponding generating function instead will be not just multiply up to 1 plus xn plus x2n. We will have multiply with all the other polynomials after that. Okay, but then here, let's get back to this particular generating function, because this will help us to simplify a little bit when we discuss the number of different partitions that we can have. Now notice that 1 plus x squared plus x cubed and so on and so forth, we can simplify it by replacing it as 1 divided by 1 minus x. Is that okay? Now for the second one we can replace it by 1 divided by 1 minus x squared. So this is exactly what we are showing here. The first polynomial, you can change it to 1 over 1 minus x. The second one is 1 minus x squared. The third one is 1 minus x cubed, and so on and so forth. Is that okay? Now, suppose that we now have n is equal to 3. So function of x is going to be like this: 1 over 1 minus x, 1 minus x squared, and 1 minus x cubed. Now, if we extract the different terms, the coefficient of different x power here, we will find that this will be equal to. So we can use a long division method or whatever to get this thing on the right hand side. So we will get 1 plus x plus 2x squared plus 3x cubed plus 4x4 and so on and so forth. Now if you see that, if you can see, now this is x to the power 4, this corresponds to the number of ways to partition 4. But here, we just have 4 here. But then if you view the original case, there are actually 1, 2, 3, 4, 5. There are 5 different ways to partition the number 4. But then we are now showing only that there are 4 different ways. The reason is that here we have restriction. Each part in the partition cannot exceed 3. So in that case, one of the case of how we partition 4 is omitted. So in that case, there's just 4 here. Okay. Now, if you are okay with this simplification, then you will see that 1 over 1 minus x, 1 minus x squared, 1 minus x cubed, 1 minus x 4, up to their infinite number of terms, this will correspond to what? This is the generating function of the terms of AR, such that AR is equal to the number of ways to partition R, to partition the integer R into positive integers. Okay. So in this case, we will have something a little bit different. So it is 1 plus x plus 2x squared plus 3x cubed plus, this time it will be 5x4 for this new function. Okay, so once we are familiar with the process, then we can do some other interesting example. So another one. Okay, how about this one? So this time it is 1 divided by 1 minus x, 1 minus x cubed, 1 minus x5, and so on and so forth, up to 1 minus x to the power 2n plus 1. So here, this is still the coefficient of x to the power r still represents the number of ways to partition the integer r. But then each part will have the property that you can have unlimited supply of 1, you can have unlimited supply of 3, unlimited supply of 5, unlimited supply of 2n plus 1. But then you can't be using 2n plus 3 and so on and so forth. So it is the generating function for partition of the integer into odd parts, so that each part has to be an odd number. But then no parts of this partition will exceed 2n plus 1. Now if you're okay with this, then this one will be the generalization or another related generating function. So if you look at this, in the denominator, there are infinite terms as a product. So here we have 1, 3, 5, 7. So this is like how many ways are there to partition the integer I into odd parts, so that each part is an odd number. There is no restriction. Okay. Okay, we will be seeing some more interesting things together soon. Okay, how about this one? Okay, how about these two? There are two different generating functions. So the first one is 1 plus x, 1 plus x squared, 1 plus x cubed, up to 1 plus x to the power n. And then the next one is similar, but then we don't have any bounds here. So it is going to be multiplying with everything. So if you look at this, then the corresponding coefficient of x to the power r in this product will be the number of ways to partition the integer r, but then there is restriction. We are only allowed to use at most one copy of 1, at most one copy of 2, at most one copy of 3, and so on and so forth, up to at most one copy of n. So the first one is the number of ways to partition an integer such that the copies, so each part has to be a distinct integer, but then every part cannot exceed n. And similarly, for the next one, it is the number of ways to partition the integer into distinct parts. So each part has to be different from the other one. Okay? So bear in mind, so what these two are meaning. Okay? Now, if you still, so now let's work out with the second one. Okay? So we have a particular, physical meaning, a particular interpretation of what is the meaning of the coefficient of x to the power r in the whole thing. And then we are going to have a different interpretation of this soon. And then, so we will see something interesting. Okay, so first of all, 1 plus x, you can represent it as 1 minus x squared divided by 1 minus x. So this part will give us 1 plus x. And similarly, 1 minus x4 divided by 1 minus x squared will be equal to 1 plus x squared. So you can replace this one by this one. And this one is 1 minus x to the power 6 divided by 1 minus x to the power 3. So we can replace this one by this one. Now, so this is going to be a product of infinite terms. So we are going to do this. Now let us observe what is going to be. So remember, we are going to multiply infinite number of items. So what do we see? What is left? So we can see also that there are terms that we can cancel with each other, right? So this 1 minus x squared, it can be cancelled with this one. 1 minus x to the power 4, it can be cancelled with some other term that is appearing in the future here. So by doing the cancellation, we will see that what is left in the numerator is nothing but 1. So we now know that if we are multiplying this infinite number of terms together, the numerator will be equal to 1. As for the denominator, we find out what is left. So we will find that 1 minus x is left, 1 minus x cubed is left, 1 minus x5 is left, and so on and so forth. Now we see this before. What is it? This is correspond to a generating function of partitioning the integer I into odd parts. Okay, now we have a very interesting thing. There is one interpretation here. We just see this, partitioning the integers into distinct parts. And then here there is another thing, partitioning the integers so that each part is odd. And then we will find that the generating function for the first one is the same as the generating function for the second one. So what does that mean? It means that the number of ways of doing one thing must be the same as the number of ways doing the other thing. In particular, we have an example. So here, this is like what we know is the number of ways to partition I into distinct parts must now be equal to the number of ways to partition I into odd parts. So this is actually a kind of a combinatorial argument, in the sense that This is the generating function for counting problem 1. This is a generating function for counting problem 2. And then we find that they're the same, so that the number of ways to do something in counting problem 1 must be equal to the number of ways that we do in counting problem number 2. Now, as a particular example, let us consider partition of 6. And then we are interested into these two restricted way of partitioning. The first one is we must partition 6 into distinct parts so that each part cannot appear again. So 6 is away, 5 plus 1 is away, 4 plus 2 is away, 3, 2, 1 is away. And any other way, for instance, 3 plus 3 should not be considered because 3 plus 3, we have 3 appearing 2 times. It is not considered. So we will find that there are exactly 1, 2, 3, 4 different ways to partition 6 into distinct parts. But on the other hand, if we now have a different kind of restrictions so that each part in the partition has to be an odd number, then we have all these left. We have 5 plus 1, we have 3 plus 3, we have 3 plus 1 plus 1 plus 1, and also the summation of 6 ones. So again, we will see that there are 4 different ways. 1, 2, 3, 4. 4 different ways. So this is like a coincidence, right? So if you have any number, the number of ways to partition it into distinct parts must be the same as the number of ways to partition it into odd parts. And you will find that if you want to get a proof why this is correct, then it is rather clueless. We don't know how to do so. But if you use the generating function of these two problems, suddenly we'll be seeing that, oh, they must have to be the same. So this is a very interesting way to prove two different counting, although they look very not similar, right? But in fact, they are counting the same, so they have the same number of ways. Okay, let's see some more examples. So this time, let's see this one. So first of all, let us consider 1 minus x multiplied with, now the remaining part is 1 plus x, 1 plus x squared, 1 plus x 4, 1 plus x 8, and 1 plus x to the power of 1 plus x of 2, x of the power, which is a 2 power. So we will have infinite terms multiplying together. Now, if you have the first two terms multiplied, you will get a product of 1 minus x squared multiplied with the remaining part. And now, when you have 1 minus x squared, it can be combined with 1 plus x squared to get 1 minus x4, and so on and so forth. So each time by doing the product of the first two terms, we can get one term cancelled. So we can see that by doing this product operation again and again, then you will find out that you can't have, so the remaining part, you can't have a term of x to, so if you look at this one, you can't have x term in the resulting polynomial because this is 1, but for every other part, it is at least x to the power 4, x to the power 4 already. So you can't have x. And similarly, this is already x to the power 4. So if you multiply this with any other thing after that, you can't have x. So the coefficient of x is equal to 0. And similarly, the coefficient of x squared, x cubed, x4, x5, they must all be 0. So in the end, only 1 can be left. So we have this, you can think of this as a certain kind of an identity. Okay, now we are going to use this identity and see two different ways of interpreting this. Okay, so the first one says, okay, so if you first now consider this 1 minus 6 to be divided on both sides, we will have what is left. We will have 1 plus x multiplied with 1 plus x squared multiplied with 1 plus x4 and so on and so forth is equal to 1 divided by 1 minus x. And 1 divided by 1 minus x is 1 plus x squared plus x cubed and so on and so forth. It is 1, 1, 1, 1, the generating function of 1, 1, 1, 1. So when you divide it by 1 minus x, the remaining part on this side will correspond to the number of ways to partition an integer into distinct 2 powers. And then, on the other hand, if you divide 1 by 1 minus x, it is a generating function of 1, 1, 1, 1, 1. So what does that say? It says that the number of ways to partition a number into distinct two powers is equal to 1. So it means that every integer has a unique representation in binary. Okay, so this is one observation, and then we get this from this generating function method. Now, for this same thing, this time let us try to divide both sides with different thing. This time, let us keep 1 minus x on one side and divide everything to the right hand side. Now, this will now become, so this, because it is not 1 minus x, it is 1 plus x, so it is going to be 1 minus x plus x squared minus x cubed, and so on and so forth. And then this one is going to give us 1 minus x squared plus x4 minus x6 plus x8, and so on and so forth, and so on and so forth. Okay, so this is minus x4 plus x8 minus x12, and so on and so forth. By the way, there was an original typo here, so it was written as 4, this was written as 8. They are wrong, so please correct it in your own slides. Okay. And now, if you look at something on the right hand side, it is not a generating function, or not a generating function that corresponds to a partition of numbers in the normal way, but we can still try to get some interpretation of what is going on. So notice that on the left hand side, it is the generating function of 1 and then minus 1 and then all zeros. Is that okay? Now on the right hand side, let us focus on a particular case. Let us find out what is the coefficient of x to the power 4. Okay. Now if I want to get coefficient of x to the power 4, I must get terms that after multiplication I will get x to the power 4. So one way to get this is 1, 1, and then minus x to the power 4. So this is one way. Is that okay? And then you may also have x2 minus x2 and then 1. This is another way to get x to the power 4. I may be choosing something like plus x4 and then 1 and then 1. So this is another way. And then I may be using another way. So this is a 1 here. I choose plus x to the power 4 and then a 1 here. So this is another way. Now, if you look at the case, so for each of the case, the resulting thing will be either a 1 or a minus 1, because the original coefficient here is plus or minus 1. So let's see when we will get a plus 1 and when we will get a minus 1. And let's also go back to the physical meaning of what is meant by choosing x4 here, what is choosing 1 here, what is choosing 1 here. Now, if you look at this, if I choose x4 here, normally we are going to consider we are choosing 4 copies of 1, 0 copy of 2, and 0 copies of 4. Is that okay? So in this case, I will have plus 1, plus 1, plus 1 multiplying together. So 4 copies of 1 corresponds to a plus 1 in the final count of the coefficient. And then I can have another one. I have 2 copies of 1, 1 copy of 2, and 0 copy of 4. Then this corresponds to 1 plus 1 plus 2. But then for this case, it is plus 1, minus 1, and plus 1 in the coefficient. So it will correspond to a minus 1 in the total sum of the final coefficient. I may have another one, 1, x4, 1. This corresponds to choosing 0 copies of 1, 2 copies of 2, 0 copies of 4. So 2 plus 2 is a way to partition 4, and we will give a plus 1 count in the final coefficient. So okay, 1, 1, 1, 1 will give us a count of plus 1. 1, 1, 2 will give a minus 1. 2, 2 we will get a plus 1. And how about the single 4? 1, 1, 4. Okay. 1, 1, 4. Okay, not 1, 1, 4. 0 copy here, 0 copy here, 1 copy here. So it's just a single 4. The single 4 here will give us a minus 1 in the count. And what else? Do I have anything else? Yeah, I may have, let me see. Okay, so I don't have any case left. So these are all the cases that we can think of. So each of the partition that we are looking at is each part, they must be a 2 power, either 1, 2, 4, 8, or so on and so forth. And then in some of the partition, we will give a +1 as the count. In some of the partition, we will get -1 as a count. So when we will get +1, when we will get -1. So a careful observation will tell you that if the total number of parts is even, then we will get +1. And if the total number of parts is odd, we will get -1. So even, what does that mean? So 1, 1, 1, 1, we have 4 ones. So we will get +1. 2, 2, we have 2 2s. So you will get also +1. And then 1, 1, 2, you will have 3 parts. So we will get the -1. 1, 1, 2, you will get a -1. Or 4, it is just a single part, you will get a -1. So this is a particular example as well. So in general, for any integer I greater than 1, strictly greater than 1, we will see that the coefficient here of x to the power I is equal to 0. Yeah, because if you look at this, is 1 minus 6 and then 0, 0, 0. And then that what does that mean? It must mean that the number of ways to partition the number into 2 powers when the total number of parts is odd is the same as the number of ways when the number of parts is even. Now, this is a super interesting observation. There is no other cleaner method that I know that you can explain why this is true. Now, as an example, so let's take a look of how do we partition 5 into 2 powers. So each part has to be 1, 2, 4. Okay. So there are ways like 2, 2, 1. There are ways like 1, 1, 1, 1. There are ways like 4, 1. And then there is a way 2, 1, 1, 1. And these two are having even number of parts, 2 parts, and then 4 parts. This one has even an odd number of parts, 3 parts, and then 5 parts. The number of ways to do the partition in the first kind is the same as the number of ways to do the partition in the second type. So this is something that is, I think, really interesting. Okay. Now, in your assignment, we are into, I think it is question number 6. It is doing just for fun, but then you will see that this type of question also appears in your exam. Okay, so I really hope that you can. So we will go over it during the tutorial next week, because it will be about homework 2 solution. So there is a technique called Ferris graph, and it is a super simple technique. So you can study it by yourself, and then we will see some example there, and then suddenly, by viewing things into 2 different ways, then we can give amazing somehow observation, just like this. So before we know the generating function method, it is really not easy to see that the number of ways to partition a number into 2 powers, such that the number of parts is odd and the number of parts is even, they have the same number of ways. Okay. Okay, now this concludes the discussion on the generating function. And let me quickly go through the introduction of the recurrence relation. So, okay, so this is the recurrence relation. So first of all, let's take a look at this sequence, 1, 3, 9, 27, 81. Of course, we now know the generating function method, so we can have a generating function for this particular sequence. But on the other hand, we can also describe this sequence, okay, in a very complex way, so that the nth term here, an, is equal to 3 to the power n. Now, this is the so-called closed form of this sequence, so that by giving you n, then you just based on n using constant number of computation independent of the size of n, you can compute the result. Okay, you just raise 3 to the power of n and then you get the result. But on the other hand, we can also specify this sequence in a different way. We can specify that, oh, the first term here, a0, is equal to 1. And then for each of the other terms, if I get the previous term, let's say an minus 1, then I just need to multiply by 3, and then I get the next term, an. So this way is called the recurrence relation, because we are describing a certain term based on the information, based on the results of the previous terms. So this is something that we are going to study in this class. Now, recurrence relation usually will have two parts. One is we talk about the boundary condition. We need to specify exactly some point that we know for certain what it is, the value of this. And then we will have the relationship between a certain term with the previous term in general. So this part, the relationship is called recurrence because recurrence talks about things in the past. So how to relate the current thing into something that appeared similarly in the past, okay? And then we have a boundary condition. Okay, so for instance, let's see another example. So this is the famous Fibonacci sequence. So for Fibonacci sequence, you will see that for each term in general, it is the sum of the two previous terms. So we can say, oh, an is equal to an minus 1 plus an minus 2. So it is the sum of the previous two terms. But to define this Fibonacci sequence properly, so we need to specify some boundary conditions. So for instance, the first term and the second term, you assume that we are going to give you this. They are not generated by this result. So we can specify a0 to be 1 and then a1 to be 1. And after that, for any n greater than or equal to 2, they can follow this particular relationship. Now, good thing about recurrence relation is they are usually very simple, and then once we have a certain term, we can easily compute the current term. And so for instance, if I want to compute an, it can always be computed, but then it may take a long time. It may take n steps or order n computation, or maybe even more to obtain the result. And then our purpose here in this class is there a way that once we have a certain recurrence relationship, we can get the closed form, so that we can get, oh, an is equal to something, so that it can be computed using constant number of operations. But then establishing recurrence relation is usually a good way of understanding the problem. So let's look at this one. So here we have a problem. We have n ovals in the plane, and then we assume that, okay, the oval may have different shape, different size, okay, but we have one restriction. We require that any two ovals must intersect at exactly 2 points. So they must intersect, and not just touching, they must intersect at 2 points, and then any three of them, they do not intersect at the same point. So we must have all the intersections between any two ovals has to be distinct. So what does that mean? So we will always see how many intersections. We must always see there are going to be n choose 2 intersections. No, it's n choose 2 multiplied by 2 number of intersections, right? Yeah, because any two of them, you will have 2. So n choose 2 multiplied by 2. And then we want to ask, if I have n ovals, how many different regions we can see that they are dividing the plane? Now, if you look at this, one oval, you have two parts. And then if you have two ovals, you can find out that there are going to be 1, 2, 3, 4 different regions. And 3 ovals, you are going to have 8 different regions. Now, if we are not careful, we may just fall into the trap that, oh, we see that 2, 4, 8. And 0 oval, it is 1, right? We see a pattern, 1, 2, 4, 8. And then we will suspect that with 4 ovals, then it will be 16. But it is not correct. Now, the exact relationship can be captured correctly by using the recurrence relation. So suppose that we use an to denote the number of regions divided by n ovals, and suppose that we have already drawn n minus 1 ovals. Now we will see that the effect of adding the last oval will be dividing we'll have this oval, the original, this, like the perimeter of this is perimeter. Yeah, the original of this oval will be divided into 2 times n minus 1 arcs, because there will be 2 times n minus 1 intersection points created, and each arc will represent a different new region that it is formed. So the correct relationship between an and an minus 1 should be an is equal to an minus 1 plus 2 times n minus 1. So although we will see that the beginning part is like 2, and then 4, and then 8, but the next one, it should be 14, and then the next one should be 22, and so on and so forth. So actually, it is increasing quadratically in n rather than it is exponential in n. So we need to be careful. So as mentioned, getting a recurrence is the big step, okay, towards solving a counting problem, because by using the recurrence relation, we can calculate the desired count step by step. So we must be able to finish the counting in finite number of steps, okay. But on the other hand, it is even better if we can get a closed form relationship. And then the study here is we are going to see some special form of recurrence relation. We can solve them easily using standard way. There are mechanical ways. We don't need to use our brain a lot. There is no observation. Just based on the recurrence, we can use a computer or whatever, use a systematic way to solve it. So the type of recurrence that we are looking at is they are linear recurrence. And also they are linear recurrence with constant coefficients. So I will explain what it means. So for a linear recurrence, it is of this form. So we can have terms of an, an-1, and up to an-r. They are related to each other in this way. So you will have an, an-1. You don't see something like an squared. You don't see something like an-1 multiplied with an-7, something like this. So every term here is just appearing by itself, an to the power 1. And then these terms can be related to each other by multiplying with a certain constant as its coefficient. So that's why on the left-hand side, we call this a linear recurrence. Okay, because it is giving a relationship about the term an with the past occurring term. And then it is linear because all the powers here is 1. And then the coefficient here is constant, so with constant coefficient. So the relationship could be equal to some function of n that depends on this n, an, okay? So as an example, so this one, 3 times an minus 5 times an minus 1 plus 2 times an minus 2 is equal to n squared plus 5. It is a linear recurrence with constant coefficient. Okay, so we are going to focus on this kind of recurrence relation and see how we can solve them by a mechanical method. Okay, so here, all these types of linear recurrence, they have one common feature. It is like if we have fixed enough boundary conditions. So for example, in this case, if we have fixed, let's say A0 is equal to something, A1 is equal to something, then based on A0, A1, we can compute exactly what is A2. And now with A1 and A2 known, we can compute exactly what is A3, and so on and so forth. So once R of the boundary conditions are determined, then we can normally solve the equation uniquely. Okay, so in general, we will see that the solution that we obtain for this recurrence relationship, the solution that we obtain here. So if you look at this, this is just a recurrence without any boundary condition given. So the solution of a recurrence relation in this form should be something that has two unknowns, and these two unknowns will be related to the boundary condition. So here, once we fix two boundary conditions, we know what each term should be. So in general, for any of this type of relationship, the solution will have two unknowns. And once the boundary conditions are given, then we fit in the two unknowns so that it will be specifically solving this. So let's see an example. Okay. Now look at this. This is an plus an minus 1 is equal to 2n plus 1. So it falls into the category. So this is linear, coefficient 1, 1 with constant coefficient. This is like the relationship is purely based on n, so this is 2n plus 1. Now, so notice that for this one, we will see that an is equal to n plus 1 is a possible solution for this one. It is a possible solution. But it doesn't mean that for any recurrence relationship, the closed form is n plus 1. It is because it doesn't make sense, because for this recurrence relationship, when the boundary, we may set a0 to be 1. So this is one way of combining this recurrence with the boundary condition. Or we may set a0 to be 17. So this may be another way to specify the boundary condition and give us a different sequence. Now, these two must have different closed form. So it means that n plus 1 itself cannot be the closed form for every possible recurrence in this case. Okay. So n plus 1, we will see that it is something that we call it a particular solution. So it will be a solution for a particular case, but it cannot be representing all the cases. Now, what we are going to do is, so this is the original recurrence, an plus an minus 1 is equal to 2n plus 1. But what we are going to do is we consider something that is similar or related. This time we set the right-hand side to be 0. So we will see that an plus an minus 1 is equal to 0 is something that we are looking at. Now for this one, we will see that for any constant a, let's say a is equal to 18, okay? Now if we plug an to be this a multiplied with minus 1 to the power n, then this will be a times minus 1 to the power n, and this will be big A times minus 1 to the power n minus 1, and they will be cancelling with each other so that it is going to be 0. One of them will be plus A, and then the other one will be minus big A, so A minus A will be equal to 0. So in that case, we will see that if I set an to be something like this, it will specify this equation. Now, you can see that this is something that corresponds to something that we call them a 0 of this recurrence relation. So in particular, if you look at this is the an that this is the particular solution that we have before, and if we combine the particular solution with the zeros that we just obtained, then this an will also be fitting the original recurrence. So if I set an to be something like this, then this whole thing, n plus 1 plus a times minus 1 to the power n, also fits here. The reason is that n plus 1 n, automatically you get 2n plus 1, and you have plus a times minus 1 to the power n added here, and also plus a times minus 1 to the power n minus 1 added here, and then they will cancel nicely with each other to get a 0. So by adding this part, you will not affect the result, the balance on the left-hand side and on the right-hand side. So if I have a particular solution for the original recurrence, then if I add the 0, so this is a 0, okay, the 0 thing to both the left and onto the term, then it will still be a correct solution for this case. So we call this is the case of the general solution that we have. So we have a particular solution, and this part, it is called this is the 0. So in math, we call this the homogeneous solution. By combining the particular solution with the homogeneous solution, we will get the general solution for this recurrence. Okay, for recurrence. And if a certain boundary condition is known, for instance, suppose that I tell you that a0 is equal to 7. Now we can plug in n to be 0 here, and then we can solve for a. So we will see that when a0 is equal to 7, then the corresponding thing will be the corresponding relationship will be n plus 1 plus 6 times minus 1 to the power n. And similarly, if a0 is equal to 8, a0 is 8, then 8 is equal to a0 is equal to 0 plus 1 plus 8 times minus 1 to the power 0. Then we can solve for a so that a is equal to 7. So if I have the boundary condition a0 is equal to 7 and the recurrence is like this, then the solution will be n plus 1 plus this a, 7 times minus 1 to the power n. Okay, as I have just mentioned, you can see that because once we have fixed a boundary condition, one boundary condition is sufficient, you get the result. So this is really the correct general form because there is exactly one variable here. So the boundary condition corresponds to the variable that we see here. Once the boundary condition is known, A0 is the boundary condition is known, then we can solve for it so that we can fix the particular variable. Okay, so here this is the name. So n+1 originally is called the particular solution because it works for a particular case. For a particular boundary condition, it is correct, but it is not in general correct. And then the an is equal to a times -1 to the power n is called the homogeneous solution. Homogeneous means that they make things that looks the same, so it is like the zeros of this problem. So by adding zeros on both sides, it is the same. We don't change. And then once we can have the particular solution and homogeneous solution, we can get the general solution. So usually we also call this a total solution. So once we have the total solution, then what we need is we find out the boundary condition, use the boundary condition to solve for the unknown variables inside, and that's it. Okay, so sorry for keeping this class long. Okay, so I hope you are doing great here. And then next week we will have the tutorial on homework 2, and then next Tuesday we will have our exam. The first exam will cover topics up to generating functions. So anything that is about recurrence relation, you do not need to worry too much about it. But on the other hand, we don't restrict you to solve a problem just by using only techniques in the part that is covered in the exam. So if you are familiar with recurrence relationship now, you can actually use this as a tool, as a technique to solve your problems during the exam. Okay? So, okay, that's all for today. Yeah, thanks for coming. So let me quickly check if there are any questions so far. Yes, for assignment 2, yes, if you can have the calculation process, yeah, it is good to include them because the tutors can understand why you have the thinking process. Okay. Okay, thanks a lot. Okay, so thank you very much. Okay. Okay, yeah. I think that's all for today. Yeah, and then see you next Tuesday. Okay, bye-bye.